All right, welcome to today's physics seminar on Wednesday, April 1st. Today by Zoom. We have Kristen Harpool talking today. She got her bachelor's in physics at Wichita State and then moved to a graduate program in Oklahoma. And that's what she's going to talk to us about today. So welcome, Kristen. And you are already sharing your screen, and I let you take over.
Thank you, Dr. Meyer. So as Dr. Meyer mentioned today, I'm going to be discussing my experiences as a Wichita State student and how they led me to my career decision of becoming a medical physicist. So it's going to be divided into two parts today. The first, I thought it would be appropriate to talk about where it began, so to speak, what experiences I had at Wichita State that led me to go down this route, a little detour that I took at the National Institute for Aviation Research at Wichita State, and then back on route to where I went on to pursue my career in medical physics. So the first thing I wanted to talk about was the atmosphere at Wichita State, in particular the physics department. When I was going to school there, it was a smaller department, but for me that was very helpful and beneficial because it made the professors more approachable. So it was easy to, stop by sometime during office hours and say hello and talk about, a physics question that I had, or even just talk in general. So the openness that the professors had and the willingness that they had to provide advice and support during classes or whatever I was interested in helped set the stage for a very open and welcoming environment for me to continue into this field. So another caveat that has always been around for since I've been going to school is the seminar talks. And as Dr. Meyer has mentioned, we have usually different professors that come in from around the country and talk about different physics topics or their research. And sometimes you get some non-traditional talks, I would say. And one of these seminar talks was actually a vendor from Sun Nuclear, and they actually make some of the detectors that we use in medical physics. In particular, I'll show you one of the devices that we use on a regular basis from this vendor, but that was my first little seed, so to speak, on the introduction of medical physics, was hearing this seminar talk from this Sun Nuclear representative who came to one of our seminar talks several years ago. So when you're in university, you have to figure out what you want to do, how you're going to get there, and why you want to pursue that degree. So my story is no different from anybody else's on that standpoint. I came to a conclusion where I was at, what am I going to do for my physics degree? Do I want a physics degree? And how am I going to continue down this route and look at different options that I wanted to do? So to do that, I started looking around for opportunities in the department to learn and increase my knowledge and experience. So the first route I had was to help be a teaching assistant. So I would help teach physics labs. And that was a wonderful opportunity for me because I was also still learning. So it's an excellent opportunity when you're teaching to be able to explain to someone else in simple terms about a concept. And if you can do that, then I believe you do understand the concept pretty well then, because if you try to explain it and it's really complicated still, and the student still doesn't understand it, you may not understand it yourself, or you need to think about how to change your way of thinking, so to speak. So for me, that was a very helpful step in my education while I was at Wichita State. It was very rewarding for me when you see that student's face light up with recognition of, oh, okay, now I get it. So that was a wonderful experience for me. And I did that for a couple of years while I was there, and it gives you good life skills and a sense of you're responsible for someone other than yourself during this time period. And I would also say towards the end of this time, I had a situation occur that altered my route from teaching to more of a practical route. So the situation that altered my route was towards the end of my second time of year of teaching. We fill out those, I forget what they're called, but they're the summary sheets that every professor and every class gets, and the students fill them out and give their feedback about the professor and the teacher, and they turn them back in. And this one in particular was a comment sheet, and one of my students, I'm not sure who it was because they disguised their handwriting, but they wrote a very inappropriate comment on there, and I didn't really know how to respond to it at the time. I had never been spoken about in that kind of a term before. It was the first time that I had run into it in the field of physics before. And so it kind of got me to steer away from the route of teaching, but I'm still grateful for the opportunities that teaching gave me, because it did lead me towards my other future career path instead. But was a key point for me in where I went from there. So the next important point that I had when I was at Wichita State was the Rocky Mountain Conference. And this was a conference that Dr. Meyer introduced to me one day. We sat down and talked about this conference is specifically for women in undergraduate physics. And I was very intrigued by this because our department being a little bit smaller, I didn't know a lot of females in the world of physics. So I was interested to get more perspective from other female professionals in our field and learn about, their life experiences and different career paths that they had chosen. So I ended up going to this conference in Denver, Colorado. And I was able to meet several of these female professionals. And one particular speaker that spoke was from the American Association of Physicists in Medicine. And she was president at the time of this organization. And so that was my second encounter with something in medical physics, so to speak. And I had it tucked away for another year before I revisited again. But she explained how she was able to still have a very fulfilling career and do what she wanted to do while still raising her family, and being able to have this well-rounded career. And that was very comforting and inspiring to me, and it made me think more about how I wanted to go a non-traditional route in physics. So not so much on the academic side of things, but maybe more on the practical side of things. So I came back from the conference feeling refreshed and ready to tackle the next adventure, except on the practical side. So this time it led to being a research assistant, and I worked with Dr. Salome and Dr. Meyer on this. And this was the Pierre Auger Observatory pilot program up in the Northern Hemisphere. So there's a Southern Hemisphere program that is set up in Argentina currently, and these tanks are set up to detect cosmic ray radiation. And so we set up another one in the Northern Hemisphere because we wanted to look at the different night skies to see how the radiation would be different. So you'll see here in these pictures, this top right one, for example, is one of the detectors that we would use, a photomultiplier tube. So I enjoyed getting exposure to that because I didn't really know about the different types of radiation detectors, but that was another crucial encounter for me for medical physics, because we use photomultiplier tubes in some of our testing. So that was another good encounter to where you just get a different exposure in a different field, and you can use it in all different areas of your career path. And this bottom left corner is what was inside of these tanks out in these pastures in Lamar, Colorado. And what we learned is sometimes what sounds great on paper and in the lab doesn't always work out in the field. So on this particular instance in Colorado, it was a pretty cold winter that year, and as a result, the water that was stored inside of these black bags, so to speak, it froze and it expanded and it popped some holes in the bags. So then we had water leaking everywhere inside of the tanks. So that led to this bottom picture where we started cleaning out the tanks and getting them all cleaned up again and trying to figure out what we wanted to do, if it was even possible to salvage this, or if it was better to just stick with the Southern project at this time. But that was important for me because I learned, not only working with other teams, and because this program was a contribution from other different schools around the country as well. It wasn't just Wichita State, it was some schools from Colorado joining in with us. So it was a hands-on effort. So a lot of teamwork was involved. So that was important to show that, you work in teams when you're doing physics, and then you learn the ultimate lesson that sometimes things don't work out, and you have to learn from them and go from there. So that was some important experience that I learned when I was being a research assistant with Wichita State. And so then I decided, once that program was kind of shutting down, that I still wanted to do practical work. And that led me to a slight detour outside of the realm of physics, so to speak, into the environmental test lab at the National Institute for Aviation Research. And I'm sure many of you are familiar with this location, but what they do is they test different parts that are supposed to go on the aircraft, and these parts have to meet certain environmental test quality standards, and those standards are set in place by the DO 160 standard. So it has different tests such as salt fog, flammability, magnetic effects. And so once that part has passed that test, so to speak, it is then cleared to put on the aircraft. So that bottom left picture is me inside of a salt fog machine, where you would put a composite material from the aircraft in it and see what the salt effects were after X amount of hours, because when the aircraft flies over the ocean, for example, you get a lot of fog and salts from it, so it can corrode the parts. So it's checking to see what kind of corrosion would occur from it. And I did enjoy my time at the environmental test lab tremendously. As you can see in that top right picture, I was able to go out and talk about the lab, and it was a wonderful hands-on experience for me. And I can even claim my moment to fame here in the bottom right picture, because I was in the Wichita Business Journal then as a result, and they took a little picture of me doing some measurements for the anechoic chamber. But I found myself missing more of the physics side of things. This still had some physics involved, but it was strictly more of an engineering kind of testing style. And so I found myself, while I enjoyed the practicality of it, I was still missing physics. So I enjoyed the experience there, but ultimately I decided I needed to do a little more soul searching and find my true passion, so to speak. So then that led to sharing the joy, so to speak. And I had to do some thinking on what I wanted to do with my physics degree. And I found myself doing a lot of late night Google searches on medical physiology. I just had little strange questions that I would have pop up, and I wanted to know more about it. So I would just Google search it, and I started taking anatomy and physiology classes for fun. And then I combined the two one night, and I found with physics and biology this job called medical physics. So from there I thought, okay, this is perfect. This takes a combination of the practical and physics, and it combines it into something that I could potentially learn more about. So this was around the time that I was getting ready to graduate with my bachelor's that I found this, and I was asked to speak at Wichita State's senior scholarship banquet that particular evening, and they wanted me to present on, a project that I had related to my major, as well as share what my experience and time at Wichita State had meant to me. And so, as we can see in our picture here to the right, I put together a presentation on our Pierre Auger Observatory, and loved every minute of it. And it was a very humbling feeling for me to be able to stand up there and share my love of physics with everyone, and explain how all these wonderful professors in the physics department made such a big impact on what I was going to do with my life. Because if they hadn't been there and not able to coax me along or give me feedback when I just wasn't sure what to do, I don't know if I would have been able to continue down this path. And so I have the utmost respect and highest gratitude for the Wichita State professors, because they helped me so much lead towards where I was going to go next in life, which was to pursue my master's in medical physics. So that led to the second part of my talk then, which is the route that I had to take. And just as a quick side note on this, before I dig into that detail specifically, just in general, I would say, regardless of what you're majoring in or what you're looking to going into, you need to do your homework on it, so to speak. You need to figure out if you actually want to do it. I think a lot of people get caught up with medical physics. They love the romantic idea of being a medical physicist, but there's a lot of hard work involved too. It's not an 8 to 5 job. There's a lot of hours involved with it. There's a lot of extra miles you have to do that you wouldn't have to do if you were going in a different physics career path or even into an engineering career path. So if you want to do it, I would recommend you should try and get some experience with it. So get some volunteering in if possible. And then you know for sure kind of on a day-to-day basis what to expect and if you want to pursue this. And if you don't, then you're not out of bad luck. You know, you're not worse for wear then. So I took some time to figure out if I wanted to do medical physics. I volunteered over the summer to make sure that it was something that I actually wanted to do. And I already had item 1 completed, which was, get your bachelor's degree, check. They do prefer that you get a bachelor's in physics. You can get it in nuclear engineering, but generally they would prefer a physics background. But if you have a STEM major, they will work with you on it. But then the next step, which is very important, when you get your master's, it has to be in medical physics. It cannot be in a different degree because the core work that you have to do there is so specific towards being a medical physicist. And while you're getting your master's, you want to look for a program that's a special accredited program. You don't want to just go to any master's program. So you want to go to a program that has been something that we call CAMPEP accredited. That's a program that has met certain requirements by this board, and they have proven to this board that they are able to teach these certain things that are required to make a well-rounded medical physicist. You'll also want to get some research experience, and when you're about halfway through your master's, you get to start applying for residencies, and that is a requirement now. It didn't used to be a requirement a few years ago, but I think about 4 years ago, they started making it a requirement that you had to have a residency before you went further into medical physics. So this is the bottleneck, so to speak, for medical physics, because there are, unfortunately at this time, there are more master's positions than there are residency positions. So they're trying to work on getting that balanced out. But one of the reasons why that happened is because it didn't used to be a requirement to do a residency, so the demand for these programs just wasn't there yet. And now that the demand is there, a lot of programs are having to play catch up to try and prove that they meet certain standards that are set by the American Board of Radiology. So then once you go through that residency application, you'll start doing some interviews. So you'll fly all over the country to do these interviews, and then you'll have what we call a match day. And that's very similar to what the physicians have to do when they're getting residencies. You have the preference that you set your preference for which institute or which school you liked the best, and then the institute will rank the candidates that they interviewed on who their preference is as number 1 and so forth, and then an algorithm will match them accordingly, and then you'll get your results and they'll say you're going to here, and that's how you know where you're going to. So once you get through all that, then you get to do a residency. And so this is more job training, more direct clinical work, hands-on, how to do your job correctly on a daily basis. And while you're doing that, you also want to start finishing up your American Board of Radiology board certification. Medical physicists really need to be certified by the ABR. They're the only non-physician job that is certified by a radiology board. And just because the complexities that we're dealing with at the end of the day, because we're dealing with radiation and we're dealing with patients' lives, the decision was made based on some incidents that happened in 2010, and the New York Times reported these articles, but it rose the awareness that when you're a medical physicist, you need to be held to some standards and keep safety in mind. But we can discuss more of that later. But once that's all done, then you get to look for a job finally. So just to kind of dig into it in a little more detail, I did, like I mentioned, I spent a summer volunteering at the Via Christi Hospital in Wichita, Kansas, and I worked with some medical physicists there. This image here on the right is me wearing my lead apron very stylishly. So what we were doing in this particular picture is all of those lead aprons behind me on the wall. Your X-ray technicians will wear these every day to help protect themselves from radiation, because radiation to your body that you don't need is bad. So we check these for the integrity of the lead-like material in the aprons to make sure it's not cracked, it doesn't have a hole in it, and we'll check those by putting those under a fluoroscopy X-ray unit. So we'll have the beam on and we'll have lead protecting us while we're checking on the screen to see if the integrity is okay or if they're starting to crack. And if they are, then we take them away and let them know that they need to order a replacement. So different things like that on a daily basis got me interested in the idea of medical physics, and I decided that this is what I wanted to do. So then I started applying to master's programs, and I wanted to go to the University of Oklahoma Health Science Center. I was really happy with their clinical experience that I had heard of, and they had a very strong residency program, so that was also important to me. And it was close to home too, as another bonus. So I was happily accepted into this program. And so I got my master's degree in radiological sciences. Sometimes the degrees may have different names, but at the end of the day, if it's radiology sciences, or it might just say medical physics on it, as long as it meets the requirements for that CAMPEP program, that's the important thing. So that's what I got my master's in. And while I was getting my master's at down in Oklahoma City at the Health Science Center, there was a lot of different good work that went involved with it. That bottom left picture is more of what I was doing for my coursework. The coursework was practical and theoretical. We were learning about detectors in this one class. So I built an ion chamber one day, and I took it to my professor, and my professor and I stuck it under the X-ray fluoroscopy machine, and sure enough, it started reading radiation when we turned the beam on. So that was a really nice, good feeling of your work bearing fruit, so to speak. And that was important because we have to know so much about different detectors in medical physics, because you'll have different vendors coming to you saying, this detector's got this for spatial resolution, and you have to look at it and you have to think critically, is this even possible, or is this just kind of a ploy to get me to buy their product? So you have kind of the core work side of things and the clinical side of things. So I was working in the clinic on a regular basis, getting familiar with the machines that I was going to be working around. And that led to my thesis, which I did in pancreatic cancer. And specifically, I was looking at different types of radiation delivery and which one would be best suited for pancreatic cancer. So that's what the image in the top right is showing. These are just some results that I had when we went to, I think that was in Washington, D.C. that year. But those are just some of the results that I had for it. And as a result of this work, it actually led me to give a talk at a symposium with other graduate students, and I actually won the Graduate Student Association Award that year. So it was against hundreds of other graduate students, and they felt like how I presented and the work that I had done was good enough to win. So that was a really exciting opportunity as well that I was able to get with my master's degree. And so once I had my master's degree under my belt, then the next question was, what comes next? So I mentioned previously on that earlier slide, you start doing the interviews and you start going to residency. And happily, I should mention that my journey through this has not always been, rainbows and flowers and really easy. It's been very difficult for me sometimes, and this is actually a perfect opportunity to mention that I did not match originally on match day, but I had a lot of interviews. So one of my interviews was with Dr. John Swanson, and he is a medical physicist down in Atlanta, Georgia, and he's been in the field really since its conception, it seems like. But he was talking to me one evening, and he just said, we were getting along really well, and he just said, I want you to know that, my program's not in the match this year, but we are accredited, And if you don't match, I want you to come to Atlanta and I want you to work under our program. And I truthfully thought he was just being nice. But it turns out I was not correct. It was probably 30 minutes after I got the results that I got a phone call from him. And he said, "Oh, how you doing?" And I said, "Well," and he replied, "I bet you've been better, but my offer still stands and I still want you to come to Atlanta to this accredited residency program." So happily, I did accept, and I did my residency in Atlanta, Georgia with Landauer Medical Physics. So just a lesson I want to point out on this is, even if something doesn't work out the first time, that doesn't mean that you should stop trying. You should always be trying to build connections with other physicists in your field, networking, just so you can build up a lot of different opportunities, because Dr. Swanson was not the only physicist who reached out to me that day. He happened to reach out to me first, but I had a couple of other physicists talk to me a couple hours later saying, "Hey, I saw that you didn't match from a program. Is there something? Can I get you into this program, or can we set you up here in the next 6 months?" So if you go the distance and make those connections with people, things are going to work out. But if you don't take advantage of opportunities and keep trying, it makes it harder to succeed. But that being said, I went to Atlanta to do my residency. It was with Landauer Medical Physics, and they have a contract set up with the Cancer Treatment Centers of America down there. So I actually worked there for 2 years under one of the physicists there that's certified, and they help teach you the ropes of what you're going to be doing on a day-to-day basis, so to speak, and that will prepare you for your part 2 of ABR certification boards. So this image here on the right might look familiar to some of you. I wasn't sure how familiar everyone's background was with this, so I was just going to try to keep it basic and expand from there. But this is a medical linear accelerator. We call it a medical LINAC for short, or really just LINAC. And inside of here is where all the magic happens, so we can produce the radiation that will treat the patient who's lying on that treatment couch. So just to kind of give a basic idea of how this LINAC works. So you have your RF power generator that generates the RF power, and while that's going on, at the top where it's labeled electron gun, you'll have a certain amount of voltage that's applied depending on the energy that you're trying to reach inside of the LINAC, and it will start generating electrons. So this is like a giant X-ray machine just for large energies. So as those electrons start accelerating along this accelerating waveguide, the RF power from the generator will creep in and meet with the waveguide, and it will help accelerate the electrons back and forth to get them faster and faster to the speed that they need to be at. And then they'll curve around this 270-degree bending magnet. And you may be asking, well, why is there a bending magnet in there? And that's because as these electrons accelerate, they spread out. So they're not nice and compact, which when we're going to be hitting an X-ray, a target to generate X-rays, we want them to be nice and compact. So this 270 bending magnet bends them around and helps make them nice and tight. So they hit the X-ray target, which is made out of tungsten, and then you'll generate your photons, and they'll come out of the head of that LINAC. And then they'll hit their patient. So there's a couple of other components that aren't listed on here, but the ISO center is something I should probably highlight here. The ISO center is the center of where the radiation is going to. So it's critical that that ISO center is lined up on the patient where you actually want to treat the cancer. So if a patient has cancer in their lung, you don't want it to be aiming at their head, because otherwise the radiation is going to go towards their head instead of the lung. But they'll lie on this treatment couch and they'll be positioned accordingly where that radiation comes out. But that's just kind of a generic idea of how the medical LINAC works. So some other concepts that we have to do as medical physicists, in addition to knowing how the LINAC works, we need to be able to protect other people from the radiation that the LINAC produces. So this is one of the jobs that a medical physicist does. You will actually check around the vault where the LINAC is housed on how much shielding needs to be put in place to protect somebody that's on the other side of that wall. So for example, you don't usually have treatment vaults standing alongside themselves. Usually someone's outside running the machine, and down the hallway there might be somebody working in an office. So what you have to do is you look at the 10th value layer and the half value layer of these materials. And based off of these values and some calculations for shielding that we use, we're able to determine how much concrete, for example, needs to be made in that particular location. So in the bottom, for example, the bottom of this schematic, we have 3.6 meters. So based off of the calculations that we've done with that equation, we would tell the construction guys, we need this wall to be 3.6 meters thick of concrete, and that will stop the beam to the radiation to an acceptable level. And to measure all of these values, there are two tools that we have on the side of here, this chamber and this Geiger-Müller counter. So these are another two different types of detectors that we use in this field to help us do our jobs. So the way you would do this is you would have the door closed so nobody's inside the vault, and you would turn the beam on, and while it's running you would be walking around the outside of the vault with your Geiger-Müller counter and with your portable ion chamber, which is what this kind of Ronald McDonald little portable chamber is. And so you're carrying your Geiger-Müller chamber around, and you start hearing your beeps, and then okay, here's some radiation here. So now I'll take my portable ion chamber and I'll measure at that spot to see what reading it is per hour, and I'll record that value, and I'll do some calculations based off of that. So that's generally how we would do our shielding. Now, it has a lot of other variables involved with it that you probably don't want to know about, but that's how you would shield a vault then, and that's one of the key jobs that a medical physicist does. And you have to check that on an annual basis to make sure that there aren't any cracks that are occurring or something hasn't changed. So this is something that you'll be doing on a fairly regular basis. So in addition to looking at the outside of around the LINAC, you also need to take care of the LINAC itself. And that's where the medical physicist comes in. So all these different tests, this is just a handful of tests here that I have in these images, but they correlate to a protocol that the American Association of Physicists in Medicine has created for us, and they're called test groups. And this particular test group is TG142, and it's for quality assurance of the medical LINACs. So it lays out, the different tests you need to do on a daily basis, a weekly basis, monthly, and even annual basis. So I thought I would just kind of explain just briefly what each test does roughly. So this top left picture is an image of a very large water tank in 3 dimensions, and that is water inside there. So we fill up the water tank and we'll put one of our chambers in there. And the reason why we do this is because we calibrate the LINAC energies with this water tank. Because the human body, it does have bones in it and other density materials, but overall, the human body is mostly made of water. So that's why we use a water tank when we're doing our readings and calculations. Now, the one here in the top middle is a different type of material. It's these little brown blocks, and their density is similar to water, similar enough that if we need to do a quick measurement, like just measure a dose at a certain point on a patient, for example, we can set up this phantom, which we call solid water material, and it's equivalent to water, so we can do a quick point dose measurement with that to see what the amount of radiation coming out of the LINAC is at that particular point. Now, I mentioned earlier on in the talk that we had a vendor from Sun Nuclear come in and give us a talk about their, what they do and what their products are. This cylindrical chamber on the couch here is one of their diode array detectors, and this detector is used to read the amount of radiation that's being delivered for a patient treatment plan. So before a patient can even start radiation, we will look at the plan that's been calculated from various algorithms, and then we'll create a plan, and it's the same as the patient plan that was calculated. We'll measure that dose, and we'll measure to make sure that the amount of radiation coming out matches what was calculated for the amount of radiation that's supposed to be delivered for that patient. So it's a safety check that we have to make sure that they're getting the treatment that they're supposed to be getting. In this bottom left corner, this is another type of solid water phantom. So the density is still equivalent to water, but it has different density plugs in it. So you have one that would represent bone, for example, or part of the lung. And we use this phantom to create a calibration curve for different materials inside of the human body. So that's how we would account for different densities inside of the body. Now, this middle bottom picture is what we call a multi-leaf collimator, or MLC for short. So the best way to describe this is inside of the LINAC head up here in this part, we have these little metal leaves that are, shaping around the target, because you want to protect other areas of the body from getting radiation. If I have radiation in my lung, I don't want radiation to go to my heart. So these MLCs help shape around that to help protect the rest of the body. But in order for them to do that effectively, we have to make sure that they're performing correctly. So this top shot is on a piece of GAF chromic film. So this is a type of film that doesn't require you to develop it in a dark room. So you can shoot your radiation field on it, and you're checking to see if the ISO center, the center of where we want the radiation to go, is in the middle and it's not spilled out like an oval. Because if it is, then we know that our treatment's going to be off. And then the other part of this bottom picture is when we've told the MLCs to go to a certain position, and we have them all going the same position. And if we see a leaf that sticks out a little too far or too far in, then we know that that MLC is not calibrated to go to the correct position. So when we run a treatment plan, for example, when we're trying to treat a patient, that MLC is not going to be in the position that I told it to go to originally. So that's why we do that test to check and make sure that the MLCs will go exactly where we're telling them to go, because then we know that when we pull up the treatment, the MLCs will go where they're supposed to go. And then finally, we have another different type of water tank that is a different machine from the LINAC. But again, because it's a calibration, we want it to be as accurate as possible. We use a water tank again to take those readings. So I've mentioned a lot about the LINACs, and I've talked a lot about taking care of the LINACs and around the LINACs, but there's more that a medical physicist does too. Another job that a medical physicist has is looking at patient treatment plans. So you'll see in the top, this is a CT of a patient, and all of these bright colors are different levels of radiation. So red means hot and blue means cold. So there's lower amounts of radiation in the blue levels, and then red, of course, is the higher amount of radiation. So when we are checking a patient's plan, physicists have to make sure that certain organs aren't getting more dose than they can get. Because nobody ever wants to give radiation to a patient unless they need it. And, radiation is very effective at treating cancer, but we don't want those other organs to get the radiation. So we use different charts that are put together by various medical bodies to make sure that they're not exceeding their limits. So for example, the spinal cord, we want to make sure no part of the spinal cord gets radiation above a certain level. And in our field, we measure this radiation dose that's delivered to the patient in gray, and a gray is equivalent to a joule per kilogram. So you want to make sure that the radiation isn't exceeding 50 joules per kilogram or 50 gray. So because if you do, you can cause the patient to be paralyzed. So in academic sense, when you're taking measurements, you don't have to worry about giving too much dose to your phantom when you're taking a reading. So this complicates things a little bit, because you're treating patients now, and you have to be careful that they don't get too much radiation from their treatment that's, you know, helping them, but you also want to help protect them from other problems down the road. And these kind of tolerances become important when a patient may come back for radiation because the cancer may have reoccurred. Different types of cancers don't all respond the same to radiation, so some don't reoccur and others reoccur, and we don't know why they reoccur. But these are all important tolerances that we have to pay attention to, and everywhere in the body has its own unique radiation tolerance because every organ in the body responds uniquely to radiation. So this is just something that a physicist has to be aware of when they're looking at a patient's treatment plan before they okay them to go ahead and start with the next step of their treatment. So we're involved with patients on the treatment planning side of things and with the LINAC itself, but medical physicists are also involved with very special radiation delivery techniques. And these particular techniques are required to have a medical physicist present because there are higher doses, higher radiation levels going to the patient in a shorter amount of time. So for this specific one, it's a stereotactic radiation delivery. And so what that means is we have, let's take this example down here on the left side. We have our tumor right here in red. And so we're trying to target just that tumor and nothing else. So due to the advancement of technology and these machines, we can conform our radiation around that tumor very well to where other organs in the body are not seeing that extra radiation. So, but in order to do that, you're giving a higher amount of dose during one treatment. And normally we don't do that. Normally we spread it out a little further because of something we call the biology effects of the cell. Cells have their own unique way of responding to radiation. So when we do this higher rated dose level to that tumor, you want physics to be present because you're giving a high amount of radiation to the body at one time. So you don't want the patient to move because you could end up delivering the radiation in the wrong location. So you want to make sure that they're nice and secure, they're comfortable, and that the dose is conforming exactly where it's supposed to go. And that's another example here on the right side in the bottom where this time the lesion's in the brain, but it's still nice and tight, and we don't want them moving around. So that's another thing that a physicist is monitoring for while they're in the middle of their treatment. And another special treatment procedure that medical physicists are involved with is something called high dose rate brachytherapy. And that's also known as HDR for short. So what this radiation source is, it's a little bit different than what our LINAC uses, because in a LINAC, the radiation is not always on. It's just like with an X-ray machine. The X-rays won't generate until you tell the X-rays to generate. But with HDR, your radiation source is a small iridium-192 pellet. And this little pellet is strong enough to treat several patients for several months for their cancer. A lot of times we'll use this device with pelvic cancer patients or prostate cancer patients. So what that happens is this little tube here that you see that extends down and into this chamber, the iridium-192 will travel down that tube and it will dwell inside of the patient for a certain amount of time that it's been told to do that. And then it will move back and it will go again to its new position. And it will continue to do that until the treatment plan that was developed for this patient is completed. Now, sometimes you have more than one tube going inside of the patient, which is what is going on up here in the left corner. Sometimes you need more than one tube in order to deliver the treatment correctly, because sometimes the cancer is spread out a little bit more. So in addition to a safety mechanism side of things and making sure that the source retracts back into the HDR holder, the physicist also has to do the calibrations for the sources. So whenever you replace that iridium-192 source, because it's a radioactive source, so it's constantly decaying. So eventually you have to replace that source, otherwise you're not going to be able to treat those patients. So once it gets replaced, you'll have to calibrate the source again. And so that's what's going on here in the bottom is this physicist is getting ready to do a source calibration on a newly replaced source. But sometimes accidents happen, whether it's during the treatment or during a source calibration. And that's why we have this little guy here in the middle with the radiation symbol on top. That is what we call a lead pig. And this is our shielded cylinder. So if an accident were to ever happen, you could take the tube or the seed or wherever it was and put it inside the lead pig and close the lid. And you'll get everybody out of the room and you'll lock it. And then you'll call your source vendor and they'll come out and actually deal with the source itself. But physicists, in a sense, are on the front lines for these kind of procedures where you have to be consciously aware of safety at all times and be aware of what you need to do if an emergency comes up. Now, granted, this is just an emergency. It should not happen on a regular basis, but you still have to be prepared for that in case something does happen. So the last part that I'll touch on for what a medical physicist kind of does in their regular day-to-day activities is what we call dosimetry badges. And these badges monitor the levels of radiation that you have. Everybody who works in a radiation oncology clinic or any kind of radiation department is required to wear a badge to monitor the level of radiation that they're getting. You should never go over your radiation limits. We have conservative limits on top of conservative limits to make sure that people don't meet these levels, but we're required to still monitor people. So this top badge you would wear on your chest, for example, because your torso has a different tolerance to radiation than your fingers do, for example, or your feet. So the other type of badge you would have is this ring badge over here on the right, and you would wear that on your hand while you're doing an HDR procedure. So all these different badges are used to monitor people and to help keep them safe, which at the end of the day, if someone asks me what a medical physicist's job is, it's patient safety. That's the bottom line. The bottom line is we are there to protect patients. We're there to protect other workers in the department and ourselves, because we are helping people get better, but we want to do it in the safest manner possible. So that's the job of a medical physicist. And you get this training when you're doing your residency. So once you have proven to your mentors at the end of the 2 years that you are competent enough to practice in the real world, you get to graduate. And I got a nice shiny plaque because my program was very nice enough to give me one. And then those are the other senior residents that graduated with me at the time. And then so once you finish that, you get to start a job process. And I applied to the Oklahoma Cancer Specialists and Research Institute, and I got the job, and I've been working there since June of this last year. So now the next job is to finish up board certification and to keep going, keep learning, and see what new developments are in the field, because the field is always evolving with new research projects or new technologies that can help patient treatment delivery. So it's a fascinating field to be in. And so that draws me to my conclusions of what I have learned so far in my life. And what I've learned is, from day one, you just have to be open to your opportunities that you have. That at the time that you're in it, it may not seem like a big deal, but all the experiences that I had in my life from Wichita State on were so influential to me and helpful and guiding me towards what I wanted to do with my career. And once you know what you think you want to do, make sure you do your homework, so to speak, and know what options are available and what you need to do in order to achieve that. Because you know, before I went into medical physics, I didn't know that I needed a master's. I didn't know that I needed a residency, and I didn't know I needed to be board certified. But once I did my homework, I figured out that I needed that. So it's good to know what you need to do in order to pursue that dream that you have. And you know, I dabbled on this third point a little bit while I was talking to you about my residency experience. Don't give up. You know, you may get shot down a couple of times, but it's a very competitive field. And if you talk to people and let them know that you want to be in the field and that you're interested in it and you have a good attitude about it, that's going to serve you a lot more in the long run than anything else. And so finally, a passion for your job will go much further than anything else. I love my job and I love being in medical physics, and I don't regret it for a second. It's been very rewarding for me, and I feel nothing but gratitude and very, very humble about all of it. So with that in mind, does anyone have any questions for me or anything they'd like some clarification on?
Thank you. That was a very nice talk, Kristen. I think we have about a dozen people or so online. So yes, if anybody has any questions, please unmute yourselves and go ahead. Matt, I think Professor Musa has a question.
Hi, can everyone hear me?
Yep.
Okay, excellent.
Yes.
Thank you for taking your time. This was a really nice talk. I just had a question. You're out of Tulsa, is that right?
Yes.
So have you done any work with proton therapy? I know in Oklahoma City they have the Proton Center there. Have you done anything with them, or?
I haven't had personal hands-on experience, but for my thesis, I actually did do proton treatment planning because that was something my advisor wanted me to look at as well. So while I haven't physically used the proton machine down there, I do know that it is something that, you know, radiologists and radiation oncologists are talking about and looking at. The biggest problem for proton therapy right now is frankly insurance and cost. They haven't really been able to prove yet, other than for pediatric patients or cranial spinal patients, that it's more beneficial than a photon or electron treatment. So that's why insurance hasn't really helped push that along. But we're hopeful that someday, you know, we'll be able to start doing protons too.
Thank you. That was my question. Thank you.
Mm-hmm.
All right, Jonathan, you have a question? Go ahead.
You mentioned that the lead aprons were made out of a lead-like material. I'd never heard that.
Well, you cut out.
You had been mentioning that the lead aprons were a lead-like material. What material are they?
That's a good question, because I remember being shocked as well when my advisor said, well, it's not actual lead, because if you were walking around with lead, those aprons are heavy enough as it is. But if you're walking around with a lead apron, you're going to be lugging your arms around everywhere. It's a PB, it's a lead equivalent, because on the tag it just says lead equivalent material. So while it's not perfect lead, I don't know if what kind of material it is exactly, other than it is labeled as lead equivalent material. It's a little more flexible.
All right, thanks. Do we have any other questions? Colleen, go ahead.
Yeah, Kristen, thank you for your talk.
Sure.
So the whole time I'm also thinking about if you could do some comparison to someone who is called a radiologist, and whether or not you would be present at the same time as a radiologist, just some of the differences, and like I said, if you work together or you work separately or what.
Sure, that's a great question. Honestly, a lot of times people think I work in radiology more than anything, but there are differences, and they're important differences. As we know, a radiologist will look at the imaging scans, and they're what we call the workers who diagnose the disease. So they're going to be the ones who find that lesion on the MRI scan or something wrong on the CT scan, whereas a radiation oncologist and the area that I'm in, we're focused on treating the diagnosis once it's been discovered. So once that lesion has been found, we'll take that scan and we'll go further along with that patient and start the process of treating them to remove that lesion and help their side effects so they can get better. Another thing that, well, actually, this would be a good time to bring this up, actually. So I didn't mention this in the talk, but there are actually two different types of medical physicists. There's an imaging kind of medical physicist, and there's a therapy medical physicist. So an imaging medical physicist is more behind the scenes. They go around to a lot of different hospitals and clinics, and they will check the X-ray machines, the MRI machines, CT machines, and they'll do what we call our annual testing on them to make sure that, you know, their dose is okay, they're still delivering it correctly, the image quality still looks good. And they do that once a year, and they don't really have a home base like a therapy physicist does. So a therapy physicist, which is what I am, you're more focused on purely just treating cancer. So in addition to the upkeep of the medical LINAC, you don't work on the X-ray or the MRI machines, but you know how they work because you're required to still take it when you're first starting out. But the therapy physicist will focus on treating the cancer. And so they'll work on just the medical LINAC side of things, making sure the patient plan is delivered correctly, and the general upkeep of patient safety on that end.
Thank you.
Mm-hmm.
All right, thanks. Kent Rowe typed a question into the chat. How do you calibrate the radiation detectors?
That's a very good question. So for absolute dosimetry, you actually need to send that off to the Wisconsin lab. Oh, what's the name of it? The National Accredited Laboratory. They send back a little certificate that clarifies this is your calibration factor. It's good for 2 years. So you can have that as your cross-reference when you're doing absolute calibration. Now, for your other detectors, you can't use them for absolute dosimetry. They're just relative measurements. But you can take a chamber that's been calibrated at this Wisconsin center, and then you can correlate your relationship from there. But in a more specific term, once you get that ion chamber and the calibration factor, what they do is they take, so all of our ion chambers have to have a temperature and a pressure correction to them because they're open. But the one in Wisconsin is closed off, so it doesn't have a temperature or a pressure correction to it. So they're able to get the most accurate representation of the reading in the chamber under certain calibration conditions that they have possible. And then that's how they're able to send that factor back to us, and we take that factor, and then we can use, if we want to cross-reference, for example, another chamber, we can stick that into our solid water setup at that certain point, and we can compare the reading. It comes out as charge, so you're reading in coulombs. So you'll read the coulomb charge that comes out from the reference chamber compared to your calibrated chamber, and that can tell you if one of your chambers is off. But you should always rely on the absolute chamber that's been calibrated by the Wisconsin accredited laboratory.
All right, pretty straightforward then.
Yes.
Well, do we have any other questions? All right, I'm seeing none. Thank you again for a really nice talk. I think we should get another update in 5 or 10 years or so and see how we're doing then.
That would be great.
This was very nice. All right, and thanks for everybody who dialed in by Zoom. This worked out actually quite well. All right, thanks. Have a good day, everybody.
Thank you.
Bye-bye.
Bye.